Hi, good evening, everyone. Am I audible?
Yes, sir.
Okay, fine, good then. Uh, Today I think we are having week 6 solve with us. Most of the things I have covered in the last week, I guess, right? So maybe before starting this session, what I'll do is I'll just uh, talk about little bit more SVD, and then we can start the solve with us. There are around 20 questions today to solve. Maybe we can do it like little bit hurry, right? We'll do that. Solve that. Okay, so I may not give you like much time because see these are like very easy questions, mostly related to the positive definiteness and positive or negative definiteness, right? Or semi definiteness. I hope all of you understood that concept in the previous session. If not, let us try and see through questions. Okay. Let me show my screen. Okay. So my screen is visible, right? I will tell you the first thing. Maybe I will just try to write it down here. The SVD form, right? So SVD form of any A. So for singular value decomposition, the matrix has to be what? Is there any condition on matrix? Can it be a square matrix? Yes or no?
Yeah.
It can. Can it be a
Yes.
rectangular matrix?
Yes.
It can be a rectangular matrix, right? Can it be a symmetric matrix? Yes, right. So any kind of matrix, any rectangular form of matrix can decomposed by using the singular value decomposition, right? And one of the and why it is important than the diagonalized matrix or the orthogonal matrices we have seen previously is that or orthogonal decomposition or the diagonalization, right? This form of matrix is like this. In this case, this U and V are what? They are the singular matrices, right? Not singular matrices. I mean to say orthogonal matrices, correct? They are orthogonal matrices. What do you mean by orthogonal matrices? The columns,
A into A transpose equal to I.
uh, or no, no. Let's say U is a orthogonal matrix. No, they are separately orthogonal, right? Like U is a orthogonal matrix and V is also orthogonal matrix. What does that
And
mean?
the columns are orthogonal.
Yeah, that is okay. One of the thing is U and let's say if U is a orthogonal matrix, then U into U trans or U transpose is I, right? That is okay. And one more thing is the columns of their like each of that matrix, they are orthogonal to each other. What does that mean is that they are perpendicular to each other. So let's say if uh, U1 is one of the columns, right? So let's say if U is like this matrix, U1, U2, and let's say U3, right? In this case, U1 transpose U2 is equal to 0, right? U2 transpose U3 is equals to 0 and U1 transpose U3 is equals to 0. So the dot product between the columns of these matrices has to be 0. Again, this also it will satisfy U transpose equals to I. Uh, okay. Or basically, this will this is satisfied when they are orthogonal matrix or orthonormal matrix, right? I think we haven't spoken about orthonormal, but that is fine. What about U? How we can form U? It is formed by using the eigenvectors of which matrix?
A into A transpose.
A transpose, and this V matrix is found by eigenvectors of
A transpose A.
A, right? And this is a diagonal matrix. And what are the diagonal entries here?
Square root of the eigenvalues.
Yeah, and they are called as singular values, right? So let's say sigma 1 is the square root of lambda 1, sigma 2 is the square root of lambda 2. So the what do you say, the highest eigenvalue, right? Is corresponding to that. Okay, fine. I think then we are fine with this. Shall we try to solve some questions? Uh, okay, then you can join using joinpd.com. Uh, this is the code KWICVI. Join using joinpd.com, and the code for that is KWICVI. Yes. We will start the questions. Sure. So first of all, try to join this using this peer deck using joinpd.com. I think, and you can put this code KWICVI without the space. Okay, let me start then. Others who have joined late, please join using joinpd.com, and the code here you can see here. This is KWICVI. Maybe I can pin down the code here. It's KWICVI. Periodic code.
Sir,
Hmm.
uh, I joined a little late, sir. Could you please explain the SVD thing once again, short,
I,
while
uh,
solving?
why the what?
While we're solving the question, after we're done solving, can you please explain SVD again?
No, I was. But there's okay. So generally, it's like this is what this is a form of matrix, right? Like SVD is decomposition. So any matrix which can be decomposed into different like three matrices, right? So A can be decomposed into three. So this like U is a separate matrix, sigma is separate matrix, V transpose separate matrix. They are formed by, so U is formed by the eigenvectors of A transpose, V is formed by the eigenvectors of A transpose A,
So
and uh,
the eigenvectors of A transpose A will be the columns or the rows, sir, for V transpose?
no, no, no. So first place V will be formed, right, and that will be the columns of A transpose A. So the eigenvectors of A transpose A will be the columns. Okay, let's say it's V1, V2, and V3. Let's say, right, and then V transpose will have to transpose that. Then they will be, so V transpose is it will be like eigenvectors of or the rows will be the eigenvectors of V transpose. Understand?
Yes,
So
sir.
uh, your V is kind of V is the columns of eigenvectors of A transpose A. V transpose is the rows of eigenvectors. Like you whatever the eigenvectors you get, you arrange them into in the rows. It's kind of like that.
Sir, where do we use Gram-Schmidt process in this?
So here we are not using it, but let's say we started off the discussion, right? So the discussion about the singular value decomposition is what we do, like what we achieve from this singular value decomposition is, if you remember from the last lecture, what we have said is uh, the orthogonal basis, right? So I have just drawn one diagram, right? So that there was this diagram here, right? And we had two orthogonal basis for, or let's say they are v1, v2. They are in which space?
Columns, row
Column
space,
space. Column space. Column space.
columns.
Correct. Or okay, column space of A, right? No, sorry. I think it was in row space of A. Row space will be in Rm, right? Okay, first of all, A is, let's say, M by N matrix. Then the row space will be what? In Rm, right? Is that correct?
Yes,
Or you can say the column space of A transpose, whatever, whichever it is suitable for you. Let us say I'll say that column space of A transpose. We have this orthogonal basis in row space of A. What you want? You wanted the, let's say, orthogonal basis in column space of A transpose, right? So you wanted to find out this, right? This u1 u2, which is the orthogonal basis in column space of A, right? By using the orthogonal basis in
row,
row space of A, right?
columns.
Or
Row.
yeah, let's say row space of A. Fine, row space of A. Like, it is better to understand. And how to find that? So we said that so each of this will be, like, let's say sigma 1 u1 will be, if you perform a linear transformation, or linear transform over these columns of row space of A, what will achieve is, we'll get this kind of, uh, so we are saying that AV should be equal to uh, u sigma. Okay. But for this to happen, we need what? We need the orthogonal basis in row space of A, right?
Yes, sir.
Correct. But let's say you have vectors, you have the orthogonal base, you have a basis in row space, but that is not an orthogonal basis. You're understanding my point? So how to find? Okay, first of all, what is the basis of R, like basis in row space of A? Basis for what? Like, if age basis, if you wanted to find in row space of A, what do you do generally?
Sir, we'll do Gaussian elimination and we'll.
Ah, right. Yes. Right. But let's say if that basis is not the orthogonal basis, so what to do now? If I wanted to make that orthogonal basis, how to do that?
Gram-Schmidt
Yeah.
process.
Here you will use Gram-Smith.
So,
Uh,
sir, we have a matrix A,
hmm,
and we want AV is equal to U sigma, sir.
correct.
You mentioned that U is the are the eigenvectors of A transpose,
Correct.
and B is are the eigenvectors of A transpose A.
Correct.
How is this related to the row space and column space of A?
Okay. Okay. How? Okay.
Sir, you don't. I'm not asking for proof. Like,
That's okay.
what
That's
is
okay.
what? Like, I'm not. I'm getting very much confused, sir. That's why.
Okay. So, okay. So the question for you is, let's say you are saying that, uh, okay, you are saying, okay, what I'm saying is, let me redefine this for you. Okay. The orthogonal basis, how will you find out? You said by using the
Gram-Schmidt process.
Gram-Schmidt process, right? Okay. Uh, and if it is not, then okay. If it is there, you don't need to do that. Now you think of this like, okay. So let us. Okay. Let's say you have this A matrix, and whatever from that matrix, right? Like, let's say if it is a rectangular matrix, what will happen in rectangular matrix? You get, let's say it is a 2 cross 3 matrix. Some vectors are there, right?
Yes,
And
sir.
you said like how we can find out its row space in row space of A, is that like you just do the Gaussian elimination,
Gaussian elimination, and we'll
you
find
will
it.
find it out, right? So instead of that, what I'm saying is that uh, these row space of A, right? Okay,
So,
that row space of A you're finding out by using the Gaussian elimination. What I'm saying is that it is exactly be equal to what, the eigenvectors of let's say which matrix, A transpose A matrix, right?
sir, just to confirm, V is the A transpose A matrix.
No, V is not A transpose A.
Sorry, the eigenvectors of A transpose A.
Yeah. So first of all, what you do is you don't do a Gaussian elimination here. What you do is you first of all find out A transpose A. Okay.
Okay,
Then find out its eigenvalues and eigenvectors
okay, sir.
and eigenvectors, right?
Yes,
And
sir.
let us say v1 and v2 are the eigenvectors of it. Let's say if it is a so if it is 2 cross 3 matrix, then in that case how many eigenvectors will you get? So A transpose A will be
Sir,
3 by 3.
V3, no, sir.
Yeah,
Three
3
column.
by 3. Yes. So you'll have 3 uh, columns, right? So you'll get 3 columns, and those will be the uh, that will be your matrix V. Fine.
Right, sir.
Now you just find out like V transpose basically, or you can do one thing. You just operate A over this V, then whatever you will get, right, that has to be equal to U sigma. That is
Yes,
what we are saying. And then if I just wanted A, uh,
yes, sir.
like if you wanted that A back, what I'll get is U sigma V inverse, right?
Or transpose, same thing, sir.
Yeah, V inverse. Why it is transpose is that because
Or
we are saying that this matrix is right. This okay, this basis is orthogonal. If it is orthogonal basis or if it is orthogonal matrix, in that case, V inverse will be equal to V
V
transpose.
transpose. So first step is to find the eigenvalues and eigenvectors of A transpose
Suppose
A,
A, correct.
and then after we find the eigenvalues,
Hmm.
uh, we find an orthogonal basis for these eigenvalues. Am I right, sir?
Yes, 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 correct. Exactly.
So that is the process. That's it.
Correct, correct.
After that, we just
Then you know the eigenvalues, and then we know that from linear algebra that A transpose A, right? So the eigenvalues of A transpose A, they are equal to eigenvalues of A transpose, right?
right.
So basically you'll get that sigma, like the moment you find out the eigenvalues for A transpose A, you'll get the eigenvalues for both of the matrix. You just have to take the square root so that they will become singular values, and you can find out U. So there are two ways to find out U, right? What are the two ways? One is like you just find out another matrix A transpose. Again, you can use the same eigenvalues and you can just
Use Gram-Schmidt process and get it. Okay, sir.
yeah. So you do that way, or you can directly find out its eigenvectors here. So by Gram-Schmidt method also you'll get it, right?
Yes, sir.
That y1, so each of these vectors, so u1 will be equal to, I think, 1 upon I think sigma 1, then a v1, right?
Right.
U2 will be 1 upon sigma 2 a v2. But what is the challenge in the here? What is the problem in here in this process? When you'll feel like when you'll find out the problem, most of the time it will work, but there is a specific condition when it will not work. When the one of the eigenvalues, right, it is 0. Correct, right?
Yes, sir.
And it is possible to get 0 because this is a rectangular matrix. In that, and when we say that the eigenvalues of A transpose A and A transpose, they are same, we are talking only about what?
Uh,
Non-zero,
Non-zero.
non-zero eigenvalues. Correct, right? So
Yes.
non-zero eigenvalues are same. Since this will have three, let's say in this case, okay, two by three. If A is 2 by 3, then A transpose A will have how many eigenvalues?
3, and this will have 2.
Two. So only two eigenvalues are same. The third one is will be what?
0.
0.
0. And if that is 0, then this Gram-Schmidt method, right? This will not work. To find out, you understand? Like or vice versa. Like it depends how
So
you.
then which method should we use?
So no, no, this is fine. You can use this method also, because let's say in this case you need only u1 and u2, right? Two vectors. So you
Yes,
just
sir.
find out the non-zero eigenvalues and you'll get it. But in case if it is different, let's say A is 3 by 2 matrix. In that case, what will happen is you will have two eigenvalues here and three eigenvalues here. So the eigenvalue of A transpose is going to be zero, right? So in that case, from this two, you will not be able to find out three eigenvectors. What you should do is you take these two eigenvalues, find out the eigenvectors, like from our normal process, right? What is that process? Suppose this matrix is K, hmm? And you know two eigenvalues. So the eigenvalue will be same for that, right? So let's say for lambda one, I'm going to find out K minus lambda one into let's say x equal to 0, right? And then you can actually find out the eigenvectors like that, right? Let's say x1 and k minus lambda 2 x2 equal to 0. This will get 2, and then k minus lambda 3, which is equal to 0. So basically kx3 equal to 0, and by these three equations you can actually find out its eigenvalues,
Got it, sir. Thank you.
right? Okay. So yeah, so let us find out the SVD form for this matrix A.
Excuse me, sir. Excuse me, sir. Hello.
Those who joined late, you can actually use joinpay.com and this code. You can enter this code KWICVI.
Hello, sir.
Yes. Hello.
Yes, sir. Uh, the answer, sir.
You can write it down there, right? There is no option.
Yes, sir. There is no option.
No option to enter the answer. Huh?
Hmm.
Okay, fine. Then you can put it into Gmeet. I'll say check from there. Okay.
Where to put it, sir?
Put it into Gmeet, possibly. If it is possible, I don't know whether you can upload it or not. Is there any option to? Okay, then keep it with you. If you can type it in here, that is fine. If it is not, just keep it with you. Let me know once you're done, so that I can, you just write down done. That's fine. Gmail. So after that, maybe I can, solve this question. Fine. I'll wait for like 4 or 5 people to write it down, and after that we can discuss. Okay. Done. Okay. Fine. So shall we see the solution then? Okay. So first step was what? Find out A transpose A, right? Just check whether it is correct or not. Is this what you got?
Yes, sir.
A transpose A is ten
No,
twenty.
sir.
Huh? No?
Different answer.
A transpose A or A transpose?
A transpose is this only, no?
Yeah, that is the correct one. So I don't know. Okay, maybe I'll find it out. What is A?
1, 2, 1,
Row
2,
wise? Row wise
1,
you're
2,
talking. Huh?
3, yes, yes, 3, 6.
6, right? Okay. Then we have to find A transpose A, which is uh, so A transpose is basically 1, 3, 2, 6, and A will be 1, 2, 3, 6. It's going to be so this is a 2 by 2 matrix again. That will be 1 plus 9, which is 10. Then 2 plus 18 is 20. 2 plus 18 is again 20, and 4 plus 24 is 28, right? 4
4
plus
plus 36.
36. So it is 40. So that will be your A transpose A. Correct. So 10, 20, 20, 40. This is the correct answer. After that, what you need to find out? Its eigenvalues of A transpose A. And how to find out the eigenvalues of A transpose A?
Det of A minus lambda equals to 0.
Yeah. So let's say determinant of A transpose A minus lambda I, that has to be equal to 0. So basically that is determinant of 10 minus lambda 20, sorry, 20, 20 and 40 minus lambda has to be equal to 0. That is
We
good.
we
Sorry,
could have taken 10 outright, sir. Can we not do that?
what is it? You can do. Yeah, that's fine. It is not so, but at the end you don't forget to multiply that, right? Otherwise, your answer should be different. Minus 400, and that is equal to 0. So it will have plus 400 minus 50 lambda plus lambda square minus 400 equal to 0. So this will get cancelled. So lambda square equals to 50 lambda. So it will have lambda equal to 50 and 0, right? These are the two eigenvalues of it. Let us see whether that is correct or not. Yes, right. So these are the two eigenvalues, and once I get the eigenvalues, I know what are the singular values. So first singular value will be root of lambda 1, that is root of 50, 0, right? So your diagonal matrix will be like this: root 50, 0, 0, 0, right? uh, and what if you wanted to understand the size of diagonal matrix, right? It should be the size of A, right? So always remember that whatever the size, right? So here it was 2 by 2 matrix. So similarly, it has the sigma has to be a 2 by 2 matrix. After that, what I should do? I should find out its eigen vectors, right? So for lambda 1 equals to 50, what are the eigenvector of A transpose?
Answer.
Yes.
What's the next question?
Okay, so next question will be find out its eigenvectors, right? So actually, this is same question. It is like stepwise we have asked to find it out. Initially, I asked you to find out what is it like find the SVD form of A, right? Instead of that, what we are saying is these are the steps which we should follow to get that final answer to SVD of A. So now let's say for lambda 1 equals to 50, what are the eigenvectors? That is, and that is what it is asked here, right? So the next step will be what? Calculate the eigenvectors of A transpose A. And my A transpose A matrix was, I think it was 20, 10, 20, 20, and 40. So for lambda equals to 50, and how to find out its eigenvectors of this matrix? It has to be A transpose A minus lambda, or rather minus lambda I into x equals to 0, right? This characteristic equation will have to solve. So here it will be 10 minus lambda, here it is 20, here it is 20, here it is 40 minus lambda times x1 x2 equal to 0 0. So that will be, we will get two equations, right? Okay, so oh sorry, first of all, for lambda equals to 50, where we'll have to find out, right? So lambda equals to 50, that means it will be minus 40 here, it is 10, 20 here, it is 20 here, minus 10 of x1 x2, and that has to be equal to 0 0. And then what you do is, maybe you can do the Gaussian elimination, otherwise you can directly solve this two equation. Both way it is fine. Let me do the Gaussian elimination. First of all, I'll make this as the uh, maybe uh, I'll do it as, like, let's say I divide it by uh, 40, right? I can do it 40, or I can do, let's say in this case I'll do uh, divided by only 2. Okay, so then I'll get minus 20 here and plus 10 here, correct? So it is kind of like this. So this row operation I am doing, r1 changes to r1 divided by maybe 2, then you'll get x1 x2 as it is. And the next row operation I'll do is r2 changes to r2 plus r1. In that case it will be 0 here and it will be 0 here, and that should be equal to 0 0. Now what I'll get, the equation I'll get is minus 20 x1 plus 10 x2 equal to 0, and that will be like x1 equals to 1 by 2 x2, right? So 1 by 2 x2, right? And then your first eigenvector corresponding to lambda equals to 50, lambda 1 equals to 50 is this one. So if I have x2 is equal to 1, then you'll have 1 by 2 here. But then this is your okay, this is your, let's say v1, right? You need to do what? You need to normalize this vector, right?
Excuse me, sir.
Yes.
Yeah.
So basically, it will be 10x2 equals to 20x1. So x2 will be 2x1.
Correct. So like, let's say this is what it is, right? So what you'll do next? So 20x1 will become 10x2, and x1 equals to 1 by 2 x2, right?
Okay.
Uh, so this matrix, this vector, and you will have to normalize this. So that normalization will be what is the length of this vector? V1
5, sir. Root 5.
Fine.
root 5. So this will become sorry, this will become 1 upon root 5. We'll have to normalize this vector. So 1 upon root 5 and then 2 upon root 5. That is my vector v1. Okay. Then what is the next step? We'll have to find out the eigenvector for lambda 2 equals to 0. In that case, what will happen? It will be 10 minus 0, 20 minus 0, sorry, no, 20, 20, and 40 minus 0 is 40 of x1, x2. That has to be equal to 0 0, right? And then again, if I do the row operations, what row operations I should do is r1 sorry, r2 changes to r2 minus 2 times r1 to make this element as 0. In that case also I'll get 10 20 0 0. That is your x1 x2 equal to 0 0. You can sense it, like what I'll get here. So the equation will be 10x1 plus 20x2 equal to 0.
Minus 2, 1, sir.
Yes, x1 equals to minus 1 by 2 x2. In that case, my v2 will be So when x2 is 1, what will be the value of x1? It is minus half, correct?
Sir, it's minus 2x2.
Sorry. Okay. I did mistake here. Right. So yeah, it should be minus 2x2. Sorry. In that case, then this vector will look like. So when x2 is 1, then x2 is 1, then you will have x1 as minus 2. Then what will be the normalized vector in this case? Is minus 2 by root 5 and 1 by root 5, right? This is my v2. It's v2. And then what will be the matrix V here? It will be the columns of this, right? V1 and V2. So it is 1 by root 5, then 2 by root 5, and here it will be V2 is minus 2 by root 5 and 1 by root 5. And if you remember, I told you initially was that A is decomposed into these three vectors, these three matrices, which is U, sigma, V transpose. And what I told about V and U,
Orthogonal.
they are orthogonal. And if you look at this, right, so the columns of this matrix V, they are orthogonal to each other. If I multiply this with this, I should get 0.
Sir,
Yeah.
sir, this one should be like organized. I think in the form of like descending.
Yeah,
You know,
because your sigma was like this, no? So it is sigma was root 50, 0, 0,
zero.
and I think it was 0. So this vector will be the vector corresponding to root 50 or 50, correct? And this,
So corresponding to root 50 will be 2 by root 5, right?
no, it was 1 by root 5, right?
Okay, my bad.
It was half and 1, and when I multiply 2 with the both, right? So I'll get 1 and 2. So it is 1 by root 5, 2 by root 5. Is that correct?
Got it.
Okay. And that
Sir,
is V. And what will be, yes, 1 minute. I'll
yes,
just
sure.
finish it out. This V transpose will be what then? 1 by root 5, 2 by root 5, and minus 2 by root 5, and 1 by root 5. Yeah. Tell me now. Yes.
Sir, assuming these two are not orthogonal, then we would have to use Gram-Schmidt process. No, sir?
Correct. Yes. If they are not orthogonal, right? At the moment you get these two eigenvectors, and if you feel that they are not orthogonal, then you'll have to use the Gram-Schmidt method to make them out.
Uh, but sir, like for A transpose,
Hmm.
since the outcome will be a symmetric matrix,
Hmm.
so anyways we'll be getting an orthogonal vector only, right?
But there is no necessity, right? Every symmetric matrix will have uh, orthogonal vectors. Is there any? I don't think so, right? I don't know whether.
Okay.
Yes,
So,
sir.
yes,
There-
I think, sir, it is for only real symmetric matrices.
Yeah.
Yeah,
So
so this is the real. Okay, yeah.
no,
So
this
A
is
transpose is the real symmetric matrix, right?
yeah. In that case, you'll get, but we cannot generalize it to any symmetric matrix. No, we don't know what kind of matrix.
Generalize.
It
Got
can be
it.
a complex matrix, no.
Yeah.
So it has to be a real symmetric matrix. We know for sure that A transpose is a symmetric matrix, but whether it is a real symmetric matrix or not, that we can't say. Correct. Okay.
Sure.
If that matrix was like this, A equal to 1, I, and 1, then we can't guarantee that A transposes or A transpose is eigenvectors. They are going to be orthogonal.
Uh,
Okay. Fine. Okay. So till now it is fine, right? All of you got the values for this as like this. We,
Sir,
huh.
sir, small question. Sir, A transpose and A transpose A, they both will be symmetric for sure.
Yes.
But we cannot say if they're orthogonal for sure.
Yes.
Okay.
But if they are real symmetric matrices, they are going to be orthogonal. No, see.
so sir,
No,
in
sorry. Okay, 1 minute. Let me clear it out. So A transpose A is going to be a real symmetric matrix. Let's say it is a symmetric matrix.
correct.
A transpose is going to be a symmetric matrix. Now, if they are the real symmetric matrix, then the eigenvectors corresponding to them, they are going to be orthogonal, right?
Yes. Correct. Yes.
Now that flow has to be there. if they are definitely A transpose and A transpose, they are going to be symmetric, that is for sure. But if they are real, in that case, the eigenvectors of A transpose A and A transpose, they are going to be orthogonal, and the eigenvectors of these two matrices are going to form the new two matrices, which are U and V. Done? Clear?
Sir,
Yeah.
I think I am a bit confused with the notations. So could you just scroll up a bit, sir?
Hmm.
Yeah, so in this decomposition equation, I do not know what it's actually called. A equal to U
Sigma.
sigma and V transpose.
Ah.
Now we found the eigenvectors, right? Is this V and that V the same?
Yes, yes. This is the
Okay,
same thing, right? This one. This is the we have found out the eigenvectors of A transpose A, and
correct,
we have arranged them into the columns, right?
correct.
And see, when we say eigenvectors of A transpose A, they have to be normalized. So these are the normalized eigenvectors of A transpose A, and
Mm,
then we got this matrix V. We did its transpose, and this transpose is going to be the same as that of this. Okay.
okay,
Yeah.
thank you.
When I just wrote this V small v2, right? So this, like, when I say this v2, this is like to denote that, let's say my matrix V is there, and there are two vectors, right? V1 and V2 of
Yeah.
this. Okay. Yeah. Right. Till now is okay. This fine is
Sir,
fine.
I have a
Okay.
small query.
Hmm.
Can you just go above? Yeah. So in the last one, sir, yeah, please can you?
Scroll up or scroll down?
Fine, sir, fine. Actually, I think it's a bit getting confused. No problem, no problem. Go ahead, sir. Carry on.
Okay. You got
Sir,
all this. Huh. Okay. Maybe I'll write down a flow again for all of you. So see, I wanted to find this part, U sigma V transpose. Okay, this is what called as the singular value decomposition. Is that okay? Then
Sir, this V transpose can have other forms also, right? If you go above.
other form in the sense,
Like, say, for example, we can also write as V transpose as minus 1 by root 5, 2 by root 5, 2 by root 5, 1 by root 5.
that is okay,
Depending
right?
on which window,
They,
yeah, yeah.
they are just multiples
Verify
of
the
it, right?
eigenvectors.
It doesn't matter.
Correct.
But see, there has to be what is it, like, orthogonal basis. So when we say about,
Yeah, got it.
right,
Sir,
so
it
Got it,
has
got
to
it.
be
Yeah, that is okay.
orthonormal,
That is
no,
fine.
sir?
not orthonormal, orthogonal. They are the orthogonal matrix.
Sir, but U and
Yeah,
V transpose both
vectors
are.
are orthonormal.
Ah, yes, sir.
The
Got
matrix is orthogonal.
got it.
Matrix is orthogonal, yes.
Okay.
sir, if the given matrix A is Hermitian, then also A
Yeah.
conjugate will have the
Yes.
eigenvectors orthogonal.
Correct. Correct. Hermitian and symmetric, right? They will have the same properties.
Yeah, for symmetric matrix, it doesn't matter whether the given matrix is complex or real.
No, 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 no. See,
Ah,
if a matrix is symmetric, that doesn't translate that the matrix is going to be Hermitian, right?
yeah, okay. If it's either Hermitian or symmetric, then eigenvectors are orthogonal.
Correct.
For both A
Correct.
conjugate or A
Correct.
transpose.
So let's say if I say that A equal to 1 I and let's say 2, right? Is this a symmetric matrix? Yes, right? This is a symmetric matrix.
Symmetric, yes, yes.
But does this matrix is a Hermitian matrix?
No, sir.
Right? So if I take a conjugate of it and then take a transpose, then I think I will get like this. So A star is going to be 1 minus I and 2. Right? Hmm? Then in this case, A is not equal to A star. And hence this A matrix is not Hermitian, but this matrix is symmetric. Okay.
Sir, one small question, sir.
Ah.
In every orthogonal matrix,
Hmm.
the column vectors, they will all be orthogonal and orthonormal to each other. Is that a correct statement?
For every orthogonal matrix.
If there is an orthogonal matrix, yes, sir.
Ah,
All the column vectors, they will be perpendicular to each other, and
this is
their
correct. The first thing is correct. Uh, the second thing may not be correct because uh, so they need not be. Oh, yeah, they did not be the orthonormal vectors. So okay, let me take some examples. So let's say A is 1 minus 2, and here it is
2, 1.
2 1, let's say. So this is orthogonal matrix, right?
Yes, sir.
Yes.
But this is not but in this case the columns are not orthonormal to each other, right?
Is it orthogonal?
So this is orthogonal matrix.
Yes, sir.
Sir,
There is one more concept of orthonormal matrix, right? In
sir,
Yes.
this uh, yes.
sir, for orthogonal matrix, orthonormal or like orthonormal itself is a requirement, right, sir?
So won't orthonormal imply that it is an orthogonal matrix?
Yes, exactly, sir.
Okay, one minute, I'll just confirm with that.
Because in any orthogonal matrix, sir, the norm is one. The norm of the column vectors are always
That is
one,
the
sir.
norm is one and it is also orthogonal to each other.
Yes, yes. All the vectors are perpendicular to each other. Yes.
Okay.
Orthonormal vector and
Okay.
orthogonal vector should
So,
be different, but matrix.
No,
so
no.
that's
Orthonormal itself implies the use of orthogonality as well as the norm is one. So both the things are included there itself.
so
Just,
actually,
I
okay, so
just checked
fine,
the
fine, okay, that is okay.
yes,
So
sir.
actually, there are two terms here, right? Okay, it's fine. I think most of the time, right? What does people do is they use this condition interchangeably. Like for example, when we call about orthogonal matrix, in that case, we say that okay, it is A transpose equals to I, and if this is true, then this has to be 1/√5 minus 2/√5, 2/√5, and 1/√5. Okay, okay, I think what we'll do is maybe we'll not make it like much complex about this. Let's say when we call orthogonal matrix, in that case this is true. So the matrix, the columns of these two vectors are going to be orthogonal to each other, plus they are orthonormal, right? So that means the norm of these vectors should be equal to 1, right? Okay, that is fine. uh, what I wanted to showcase is, sorry, can I move further? If
Yes, sir. Yes.
Yeah,
Clear,
I
sir.
Row should also be normal, orthonormal.
rows not required, na? Why rows? I think okay, but still I think they will become, but I don't know whether that will be the case or not, but at least the columns we can say for sure. Okay, let me finish this
So
first
can
and
you
just,
check for A transpose here?
what should I check?
Is it equal to identity?
You can check, na? Huh?
That condition should be satisfied.
It has to satisfy, right? It's a symmetric match. I'm saying that it has to satisfy. You should also check, right? Or do I need to?
Yeah, yeah. So that is what I'm saying. For that, for you check for A transpose, right?
Okay, step. Okay, you can do it later. I'll just write down all the steps. The step one is what is it like? Find eigenvalues of, or possibly okay, I'll do one thing.
So may I ask a doubt? Maybe not related to this what we are discussing.
Uh,
The reason how like why we are coming to this.
uh,
So in case of if it was a square matrix, we had a option like A is equal to S lambda S inverse, right? And in that case also
no,
S is
okay,
orthogonal.
one minute. What
Huh?
is it? What is AS?
No, I'm just trying to correlate. Like we ultimately wanted to kind of reconstruct. We wanted to break one matrix, right?
Hmm.
Now, in that case,
Hmm.
where A was a square matrix, there we have this diagonalization equation S lambda S inverse,
Hmm. Hmm.
and here we have this SVD equation where A is equal to U sigma V transpose.
Hmm.
So both these kind of can break the actual matrix into component. So what I'm asking, sir, like uh, in case of a square matrix, should we go with this diagonalization equation, or we have to? I mean, just in real time, if we have to have this kind of, if we have this situation, what is the correct thing to do? Here, I understand that we are doing a SVD
So,
problem
okay,
solving.
what is the difference between the diagonalized version of it, right? Diagonalization, when we do the
Mm-hmm.
decomposition there and we do the decomposition here, both are the decompositions, right? And I think if you if you know from linear algebra part, there is one more decomposition which is Q lambda Q transpose. I don't know whether you guys have. This is not the part of our syllabus, but this is one of. So there are three types of decompositions. One is one more is there, but let's see. This is one thing. This is SVD. This is Q is what? These are the uh, orthogonal matrices, right? So Q and this lambda will be there, and here we use the eigenvalues, and there is one more which is S. I think lambda
Yes,
SV.
inverse. This is the one we
It is
have.
diagonalized, right?
Yeah.
But the differences between these three is and when to use, right? So why this is not preferred most of the time is what the eigenvectors of this, right? This matrix S, they are not orthogonal to each other. Understand? So orthogonality is one of the important criteria in dimensionality reduction. If you so next week we are going to learn about PCA, which is principal component analysis, right? Where we wanted these projections of all the data points onto some eigenvectors, and if the eigenvectors are orthogonal to each other, then what will happen is, so let's say if you okay, which one will you prefer, right? So let me ask one question to you. Let's say these are the two vectors A and B, right? They are not orthogonal to each other, and there is another vector A and B. If they are orthogonal to each other, which uh, which two vectors will you choose, uh, let's say for decomposition, if I wanted to do any decomposition?
I
Ortho.
think A and B orthogonal one we will go with.
Right, ortho will go with orthogonal. The reason is what?
We'll be able to reduce the number of dimensions, right?
Correct. Yeah. Right. So that is what people why they go for SVD is because SVD gives you the decomposition in which the vectors or the matrices also are there, right? They all are orthogonal to each other, right? So these U and V are the orthogonal matrix. So in that case, uh, it is like that way it is a good matrix, right? Linear algebra point of view, if you think. And this is not
S-
the case with this matrix, the diagonalizable matrix.
so second one, second decomposition only used in real symmetric matrix. Na?
Second what? Second?
Second one, decomposition Q lambda lambda to the transpose. It is only for the real symmetric.
Right, right. Real matrix. Yes.
Real matrix or a real symmetric matrix? Because
For A, this Q sign. Yeah,
uh,
it should. So that A matrix should be symmetric and positive definite. That condition also is there. So it has to be
the
positive definite.
second one we have only read before. This is for
Yeah.
all
So
real
this
matrix.
is for rectangular matrix. Okay. This is for symmetric and positive definite, and this is for only square. And that is also one of the reasons that this is going to be a like the choice for decomposition, right? Because this SVD we can do for any kind of matrix. If any matrix is there, we don't have to worry about it. We can actually get the decomposition of it.
But sir, first one is the SVD equation and the other two are diagonalization equation.
That is okay, right?
Yeah, okay.
uh, that doesn't matter, right? See, decomposition is like any matrix, right? If I can be able to showcase, or we can be reconstructed using some other matrix. That is what decomposition means. And that's why, so these are the different methods, and why we pick the one SVD is because this gives me the decomposition for any kind of matrix, any rectangular matrix. Okay.
Yeah, okay.
Okay, so step one to find is find A transpose A, the step 2 will be find the eigenvalues and eigenvectors corresponding to these eigenvalues for A transpose A. Is that okay? And then step 3 is either you can use that Gram-Schmidt method to find out so once I find out the eigenvalues of this matrix, can I find out the diagonal matrix? Yes. You can find out diagonal matrix just by what? By finding out
Square root.
singular values. Right. Singular values are basically the square root of eigenvalues, right? Like that. And then step 4 will be what? Either you can find A transpose, and step 5 will be, let's say, find out its eigenvalues. Oh, you don't need to find out now, right? Because the eigenvalues of A transpose and A transpose are same, so we already have found out the eigenvalues. Just find out the eigenvectors, right, of A transpose. I hope this is clear. Okay, right. That's now. I think we have completed this part. We'll have to construct this Q2 transpose. How to okay, this, and then how to find out Q1. Q1 is what? Here in this case, Q1 is U, right? So see, this was the relation, right? X1 is what here? The eigenvector corresponding to don't remember.
Transpose A. B.
Yeah,
X1
yeah.
is U,
V
right?
V. So Y1 is corresponding
Y1
to
is
U,
U.
and X1 is corresponding to the
V.
largest eigenvalue of V, right? So that into this, and 1 divided by sigma 1, if you do it, you'll get uh, the first vector of U, right? And y2 will be like this, but then sigma 2 equals to 0, right? We have found out that, like, let's say if sigma 2 is 0, then what will happen, right? So that in that case, we know that y2 and y1 are orthogonal to each other. So if they have to be orthogonal, then what is the criteria? So this was 0.3162, 0.9487. You can directly get this minus. That is fine, right? Is okay. I hope you understood this part. Or else the second method is what? Find out A transpose. We know the eigenvalues of that, and just find out its eigenvectors. Is that okay?
So can you repeat the lambda to 0 when?
Okay. Okay. So, oh, so here, if your sigma 2 equals to 0, what does it? Okay, what are the eigenvalues here? We have got for eigenvalues of A transpose A are what? They are 50 and
0.
0. So in that case, sigma 1 will be what? Root of 50, and sigma 2 is 0.
0.
Now, if the and from Gram-Schmidt theorem, what I know is okay. What is V? It was, I think, 1/√5 and 2/√5, and here it was minus 2/√5 and 1/√5, right? So from Gram-Schmidt theorem, I know that A. Uh, so okay, let's say y1. Okay, U is, let's say I'm saying that U is y1 and y2, right? Okay,
Oh, yes.
y1 and y2. These are the two vectors, right? So y1 will be what? 1 upon sigma 1 to A. What is it?
X1.
So let's say this is x1 and this is x2. So x1, right? So 1 upon sigma 1 is what? Root 50.
50.
What is A?
1 by root 5.
No, no, no. A original matrix. I think 10.
Oh,
What was that?
10. 20,
20, 20, 40.
No, this one, this one.
1, 2, 3.
1, 2, 3,
1,
6.
2, 3, 6. It is 1, 2, 3, 6. This A, and x1 will be
1
this
by root 5,
1 by root 5,
2 by root 5.
2 by.
1 to 5.
So if I multiply that, what I'll get? 1 upon root 52. Sorry, root 50. Here it
Root,
is
root 5.
5 by root 5, right? And basically that is going to be root 5, but let me write it down. 3 plus 12 is 15 by
15.
root 5. That basically is going to be 1 upon root 50. So 5 by root 5 is root 5, and 15 by root 5 is 5 into 3. So 5 is
3
like
root,
3 root 5.
3 root 5.
Okay. And again divided by root 50. So what I'll get? The final one is 1 by root 10. Is that fine? Because it is root 5 divided by root 50. In that case, root 5 will be here. Root 50 can be written as root 5 into root 10. So this 5 will get cancelled. 1 by root 10. And here it is 3 by root 10. Is that okay? I hope this is fine. Now, how to find y2? Y2 is 1 upon sigma 2 a x2, right? But sigma 2 is 0. A is your 1, 2, 3, 6. And what is this x2? It is minus 2 by root 5 and 1 by root 5. Suppose I do this calculation, that is fine. But what is here? Is infinity, right?
Yes, that's the
So
point.
I'll not be able to get. But in that case, so what it is said to me is that if sigma 2 is 0, but I know that that y2 is perpendicular to y1, correct? What does that mean?
These are orthogonal to each other.
So if they are orthogonal, and how to what do you say about it? Y1 transpose y2 equal to 0,
0.
right?
Yes.
So if this is my y1, so y1 is what is it? 1 by root 10, 1 by root 10, and 3
3.
by root 10. So now what will be the perpendicular vector to this? It will be minus 3 by root 10 and 1 by root 10. Why? If I multiply this, if I do this uh, dot product, then I should get 0. So you can check it out. So what will be y1 transpose? It will be 1 by root 10 and 3 by root 10 multiplied with minus 3 by root 10 and 1 by root 10. So this is minus 3 by root 10 plus 3 by root 10. So equal to 0. And that is why if this such case occurs, what you should do, or you should know that these vectors are going to be perpendicular to each other. I just have to find out its orthogonal vector. So that's how you can find it out. What was the other way? If I don't want to do this, find out A transpose and then find out its eigenvectors. For the IA transpose, what are the eigenvalues? They are going to be same, 50 and 0. And I have showed you how to find out the eigenvectors already, right? Is that okay? Just check whether you guys have done the calculations correctly. We can move. Now then we can reconstruct this. So Q1 sigma and Q2. Q1 basically is U. Sigma is this one. Q2 is basically V transpose. So if I just do it, you can see that these values, right, they are like very closer to the actual matrix. So we are able to reconstruct the matrix using this 3 decomposed matrix. Okay, so next question.
So in that review yesterday, I think Thursday's class, you took that approach, A transpose and A transpose A, and then
Yeah,
finally we.
no, that is like, see, in case you don't understand the Gram Smith, right? That is like the sure shot you will get the correct answer, right? That's why I used it there. So you can use either of it. It's okay. Nothing will stop you from doing that.
But that which
Actually,
this previous process is a bit lengthy, I think. But
Yeah,
Gram
yeah,
Smith.
yeah. That's true. That's true. Gram Smith is like a little bit easier.
Excuse me, sir.
Yes.
In the calculation of eigenvectors, so find if I have a vector
Your voice is not coming correctly.
hello,
Ah.
hello, I'm audible. Hello.
I think your mic is having some issues. I guess.
Hello.
Yes, you're audible, but some of the words I'm not able to hear properly. Yeah, go ahead. Or maybe you can put it into the chat. It's fine. I'll read it out.
Sure, sir, sure.
Yeah. Okay. So in the meantime, just solve this question. Which of the following is an stationary point?
A is a very
Right. How to find out the stationary point?
First derivative.
first derivative would should be 0.
Yeah. So your question is f of x y is x square plus y square, and the del of, right. Why should I use del of f of x y here? It's not like f del.
Partial derivative.
Yeah, I'll have to take the partial derivatives. So that will be del f by del x, del f by del y, and del f by del x is uh, so it is 2x here, right? In that case, I'll have to treat y as constant, and here it is 2y. It's not minus, okay, right? And then okay, and what do you do? Let's say if we generally, what is the flow? You are given f of x. What do you do to find out the stationary points? You equate this the first derivative with equal to 0, right? Here also you have to equate it to 0. So that is 2x equal to 0, y equals to 0. That gives me x equal to 0 and y equal to 0. These are the stationary points. Okay, right. Let's move ahead then. Okay, so now for the same question, it is asked that the stationary point of the function is minima or maxima.
Minimum.
Yeah. Yeah, now you can, I think, write your answer into this join PD, right? I think it is there. You can write it down. Question is, does signs matter if I have x equals 2 by and I no, both of them are fine. Both of them are okay. Uh, as long as your signs are like correct, right? So this 1 and 1 and minus 1 is correct. Again, one more thing to remember here is you make it have to, like, you'll have to make that vector normalized, right? So it should be, if it is your eigenvector there, it has to be 1 by root 2, 1 by root 2, and minus 1 by root 2, minus 1 by root 2. This way, but this will not be correct. One, I think that also 1 1. If your vector is 1 1, it cannot be minus 1 minus 1 plus 1 or 1 minus 1, right? So whenever you are changing it, so basically what you have done here is that vector 1 1, you made it as minus 1 1 1. Like how does you do that? You just multiplied with the scalar, which was minus 1. So minus 1 into 1 1 will be minus 1 minus 1. This is fine. This is okay. That's not a problem.
Sir, but I translate to answer line differing.
Oh no, I'm not. Anybody is able to hear him properly? I'm not.
His voice is breaking, sir, not coming
Yeah,
clearly.
clearly. That's what. Yeah. Okay. What is the stationary point of the function?
Critical point.
Saddle point or cannot be determined?
Minimum.
Minima? What is the condition on minima?
Second derivative.
Second derivative is positive, right? Greater than
So
0.
no, that is for your. So if it is greater than 0, that is your minima.
Minimum.
If it is less than 0, it is maxima. But when you have two vectors, in that case, it will not be that one, right? So you have to find, let's say, del f of x equal to 0, del f of y, del y equal to 0. That is yours to find out stationary points. Then what you will have to find it out? You'll have to find out this, right? Del 2f by del x square, then del 2f by del y square, and del 2f del x del y, right? 0, 0, and 0
Del
here.
2 by del x square will be 2, right?
Sorry, sorry. Okay, okay. Wait, wait, I want. So it is two. And what about this? I think it is zero.
Zero.
So if this is equal to zero and if this is two, in that case, what will be condition? You know, right? I think you guys have.
As per Hessian, the matrix determinant will be greater than zero, right?
So Hessian is
So it will be
zero.
minima, right?
Cannot be defined if it is 0.
It is four. It is greater than zero, and if it is minima,
Minima.
Yes, yes.
right? Is minima, right? Okay.
Excuse me, sir.
Yes, yes.
We need to do double differentiation and then.
Or yeah. So basically, to find out in this case, it is like you'll have to construct a Hessian matrix. Hessian matrix will be looking like this: del 2f by del x square, del 2f del x del y, and it is going to be a symmetric matrix, right? So Hessian is a symmetric matrix, and you have this. Sorry, this del 2f del y square. Yeah, and then if this the determinant of Hessian matrix is greater than 0, we'll have minima. Determinant of Hessian matrix is less than 0, we'll have maxima. If determinant of Hessian matrix equal to 0, what you'll get? It's a saddle point, right?
Sir, inconclusive, I think.
No, no.
Inconclusive. When it is less than zero, it is saddle point.
Less than zero inconclusive.
Less than 0 is inconclusive, right?
Saddle point equal to 0, if I remember correctly, it's inconclusive.
Is it?
Yes, yes. Same thing.
Equal to 0 is inconclusive.
Okay, okay, fine. Okay, I think I forgot.
Equal to 0 is saddle point, I think.
Okay.
And then less than 0 is minimum.
saddle point.
Less than 0 saddle point. Okay, fine.
Yes, sir.
I just forgot, I guess. You guys know it, right? I'm going with your intentions, right? Okay, maybe I just forgotten that. It's fine. But yeah, so okay, maybe if I go with that, so this condition is uh, minima. This is maxima. This is indefinite or inconclusive, right?
Saddle point, right?
This is saddle point.
Check.
Right?
What's the difference between second and fourth, sir?
Huh?
What is the difference between the second and fourth? You have listed four conditions.
I said there is a second condition for
Yeah.
the minima and maxima. The
Huh?
pivot should all the leading pivot should be
Leading pivot should be greater than
for
zero.
minima and less than zero. Less than
F
zero.
of XS.
Actually, their order has to be checked 1 by 1, then 2 by 2, and in the entire.
No, that is like positive definiteness. No,
Sorry. Yes. That counts.
that is different, right? This is like calculus.
Yeah. There we can check the signs of this elements basically. Del square up by del x square. Then del square up by
Positive. They all has to positive.
yes.
Okay, I think if I remember it correctly,
Sir, for maxima, I think the second order differentiation of x should be positive, and for minima, the second order differentiation of x should be negative.
No, it is opposite of that, I think.
okay, let me.
Oh,
check.
yes, opposite of that.
Let me check it.
For minima, I think second order differential should be positive.
Yes.
Yes.
Minima positive and maxima, yes, it's other way around.
Yes. My
I forgot actually.
Okay, so okay. This inconclusive is for determinant of h equal to 0, right? Local minima is if this is positive and okay, I'll write it down properly.
Sir, you are complicating things.
I am complicating it.
No, you are confusing.
No, I'm confusing you or I'm getting confused. I don't understand. Okay. Del 2f upon del x. I am confusing you guys or you are I'm getting confused.
No. All right.
All right. So for minima, right? that for minima, determinant of h, right, has to be
Greater
positive
than 0.
0,
Positive.
and your del 2f upon del x square should be positive, and del 2f upon del y square should be positive. Okay.
So that is enough.
It is not.
Plus
I
plus
think only two condition is
for
okay.
two variables is enough.
Right. We only need to check for x only.
Yeah, so that is okay. Like I'm just writing it down. You can just check it later. So here also for maxima it has to be greater than 0. Uh, then what is it?
Less than 0.
It is less than 0.
Less than 0. That is your maxima. Then for saddle point, determinant is again positive, right?
Less than 0.
No,
Positive.
negative. Determinant should be negative.
So determinant has to be negative, and oh no,
That is enough.
that is fine. Yeah, so that has to be correct. So it has to be like this, and then we have inconclusive or indefinite, right? So whatever
Equal
inconclusive
to 0.
is when you have determinant of Hessian matrix equal to 0. Fine, you can just follow this, and that will be fine, right? And the same thing is there for your. Sorry, there are a few different things for definiteness, right? Positive definiteness we have discussed earlier. Okay, done. Now, can you find out the stationary point for this, whether it is maxima or minima?
It is saddle point.
Maxima.
No,
Find it out. Okay, I'll just take two
no,
minutes.
no.
Sir, how many questions are there in total? Hello. Hello.
Yeah. So just a minute. I'll just okay. Minus x square minus y square. Now I'll solve this equation. After that, I will not solve maybe for next questions, right? So my del f by del x equals to what is it? Minus 2x. Then del f by del y equal to minus 2y. To find out the stationary points, we'll have to equate them to 0. So the stationary point will be x equal to 0 and y equal to 0. This is my stationary point. We'll have to check whether these stationary points are it will get the maximum or minimum. For that, I need to find out the Hessian matrix. Step to do that is find out the second derivatives for this. So my first derivative was the partial derivative was minus 2x here. So if I find out its second derivative with respect to x, then it will be minus 2. Here it is del 2f by del y square will be again minus 2 here. And one more thing we need to find out is del 2f by del x del y. So either you just maybe for this quantity you just differentiate with respect to y, or uh, this quantity with respect to x. And if I do that, I'll get what? 0 here. So Hessian matrix will be what? It is minus 2, 0, 0, minus 2. Now what is the next step? I need to find out determinant of h. You will have to, so let's say if you had the quantities like this here, 2x, 2y, what you should do here, you will have to plug in this
Find at
value.
0, 0.
Yeah, but right now these quantities are free of x and free of y, then we don't need to worry about it. So just find out its uh, determinant. So what is the determinant here? 4, which is greater than 0. That's fine. Now what we'll have to look at for del 2f by del x square, whether it is greater than 0 or less than 0. It is less than 0, and then it will have, then I can conclude that it is having maxima as per these conditions, right? Okay. Okay, I think that is fine. Maybe okay. So it is having maximum. Okay, and this graph will look like this. So yeah, definitely it is going to have maximum. Okay, you guys can find it out for this. Maybe I'll not solve for that. You just write down your responses here. I will read those responses, and we can move forward.
So could you show that conditions once again? Yeah. So minima is both are greater than zero.
No, no, no.
The second
It's not. It's
sentence.
or, actually. It is or. Either you can check for this. The same thing is here also. It is or. It is not
Okay.
mandatory to, Sorry.
So can it be like one of it?
Yeah, yeah. You can check for one. That is fine. Don't have to worry about it. It's fine.
I didn't actually understand. So let's say the dou square f by dou x square. I mean, second partial derivative with respect to x is greater than zero,
Hmm.
but with respect to y, if it is coming as negative, I
That is
mean,
not going to happen.
it's not going to happen.
Either
What is
this
it?
quantity is going to be greater than zero, or either they are going to be less than zero if the determinant is positive. See, if you wanted to get the determinant positive, see in both the cases, right? You see that determinant of h is greater than zero and determinant of h is greater than zero.
Correct. Yeah.
If one of the quantities is negative, right? Not
Multiplication.
going to
Okay, got
be.
it. Yeah,
That is why that is not going to happen. So that's why we can check either this is greater than zero or this less than zero. At the same time, so when this is negative, right?
yeah.
The other one also be negative, right?
Correct, correct. Yeah.
And this is positive, that other one also be positive. So that is the meaning of it. Hmm? Okay.
Yes, yes. So, but we also have that dou square f by.
Okay.
Okay, so let me. If I come across such a case, I'll ask. This is fine. Thank you, sir. Yeah. The question.
Okay. Okay. If you join using join PD, right? You can see that question.
Yeah, yeah, yeah. Okay, yeah. Thank you.
Sir,
Hmm.
what are they waiting for? There is
Hmm.
less time. There is only half an hour time. There are
No,
many
no,
questions.
these questions will be like simple one, right? So most of the questions are like this only. Finding out minimum, maximum, the suitable for positive definiteness and all. I think we'll finish by 8, 8:15.
Yeah. Yeah.
We have another class at
So
8.
where
Yeah, we
where
can
can you submit answers? It is not showing.
joinpd.com. Go to the joinpd.com and then
Oh, okay.
this
Okay.
KWS. Okay. Yeah, yeah, we'll finish by 8 o'clock. We'll try to finish. If you can just answer me directly, that will be fine. So it is. I hope
Sir,
uh,
sir, one small question, slightly off topic.
mm,
Sir, in last class you mentioned that to identify if a matrix is positive definite,
mm,
then all the pivots should be positive after doing row reduction.
correct.
Sir, what do you mean by this, sir? Like after doing row reduction, we have to see which columns are the pivot columns, and if those
Yeah, yeah, yeah. What are
pivot.
the pivot? Yes, yes. What are the pivots, right? They have to be. And see, one more thing is uh, that positive definiteness. It is only for which kind of matrix I said to you, right?
Symmetric,
And
ortho,
so no,
symmetric,
symmetry is fine.
real,
If the
real
symmetric
and
matrix
symmetric.
is there, will that be a square matrix?
Square and symmetric. Yes, yes,
Yeah, so that will not be a rectangular matrix anyway, right? So
yes.
whenever you will find out the pivots, you'll get like so the pivots will be kind of like that. You'll understand that from there those pivots. Right? Let's say if it three by three matrix are there, how many pivots you can find?
So
Maybe
suppose there are two pivots and the last one is just zeros.
yeah,
Then
yeah, that's okay.
how
So
to check?
in that case, the two pivots has to be positive.
So we have to go back to the original matrix and see if those two pivots are positive. Because in row reduced, everything will be 1, 1 and 0, no, sir?
No, no, no. See, I am not saying about RREF. I'm just talking about REF, row row echelon form.
Sir,
So
even in row echelon form, all the pivots will be 1. And
no, that is like so one is also positive thing, right? One actually it is not like always one. You make them as one, right? You can keep it as it is. You don't need to be like make always one, right?
sir, can you show with a small example, sir? A very basic one.
Okay. See, when you talk about that, right? So how can I consider matter? But okay, let me do something. You can see okay. I'll tell you the most of the team, right?
Sir,
No, I'll
suppose it is
no, I'll solve
minus
this.
1, minus 1.
I'll solve this. That's not a problem for me. Thing is, whenever you get a question, right? So I'm telling you
Yes,
like how to study is that whenever you get the question, right? Try to let's say you have this doubt, right? I knew that okay, whether it is possible or not. In that case, don't wait for someone to answer for you, right? You just try to find it out, and if you are not able to get that, then you can ask, right? So my worry is not
okay, sir.
like this part. Like, it's fine. Okay, let me try this for you. Let's say it is 2, 5, uh, 4, and let's say uh, 6 or something, right? This kind of a matrix.
Sir, can you put it as minus 2
You
just for a
take
little bit of
it,
clarity?
it doesn't matter. What the question for you is what? The question is you said all the pivots are either 1 or 0, right?
Yes, sir.
How can is that possible? Let's say if I just do second row is made to R2 minus 2 times R1. What I'll get? 2, 5, and 0 and minus 4. So what are the pivots here? This is going to be pivot and this is going to be pivot, right? Let's
Okay.
let's you do one more thing. Like R2 changes to R2 by minus 4. What do you get? 2, 5, 0, 1. Right?
Yes, sir.
Now you can argue that maybe one is on this pivot or this pivot, right?
Yes, sir.
Right, but you don't need to do that. So you actually made this one by dividing it here, right?
Okay, sir.
You have to keep these things as it is. You don't need to uh, because this another row operation you are doing, right?
Yes, sir.
Now
Sir,
so now you'll say that these two are the positive pivots,
got it, sir.
but this is not
But
the case, right? This is
yes, sir.
positive and this is negative pivot, right?
Yes, sir. Sir, so here, suppose in the example, if it was minus 2,
Then directly so that
one of the pivot is negative.
so
Yes, sir.
in that case uh, you can actually talk about it. So then again, the most important understanding of it is you have the two other tests, right? So basically, don't go for the pivot test. The pivot
Okay, sir.
test may not, because see, if you're not understanding this properly, like what are the pivots and all, then it will be a difficult thing. Either what you will have to do is you will have to think about these two uh, other tests, which is one eigenvalue test and determinant test.
Determinant.
That is like basically will give you the right answer, right? So that is what
Okay, sir.
the thing is.
Sir, one more small question, sir. Theoretical question.
Hmm.
A positive definite function is a function which is always greater than 0, and at x is equal to 0, it should be 0.
X is what is x here?
X comma y is equal to 0 comma 0, then the function value should be equal to 0.
What is x y here? That's what I'm asking.
A positive definite function, sir. Let us say x square plus y square. F of x comma y is equal to x square plus y square.
So okay, x transpose ax, you are saying that here if
No, sir. I'm talking about function, sir. I'm talking about a function. Positive definite function, not matrix.
what is positive definite function? I'm not.
Sir, in one of the lecture videos, he explains the professor explained. I just
See, I think, see, that's what you are confusing something. So let's say x is going to be, let's say x is this thing, right? And let's say if I'm talking about like matrix A is a 2 by 2 matrix with A, B, B, C. Okay, is that fine? Hmm?
yes, sir.
Now, if I solve this, it will be xy here. Then here it is A, B, B, C. Then you have xy here, right? And then what I'll get here is xy. This will be what?
Ax square plus 2bxy
This is
something will get.
ax plus by and bx plus cy. Right, and then you will get this equation, which is ax square plus bxy. So it is basically 2bxy and plus cy square. Now this equation, right? In that case, if this polynomial, right, if this is going to be greater than zero, then it is positive definite. And it's greater than or equal to zero, it is positive semi-definite.
Sir,
And
but and just my small clarification was that x and comma y is equal to 0 comma 0, then the function value should be equal to 0.
that is anyway going to be zero, right? You just plug in that x and y equal to zero.
Sir,
So
suppose
for
plus.
any other values than x and y equal to zero, right? That has to be follow. For x and y
Okay.
equal to zero, it is good. So whatever equation you will get always zero, right?
Yes, sir. Okay, sir.
Correct, na? See, if I put x and y equal to zero, you do any polynomial, it's going to give me value zero. Apart from this zero
Sir,
zero,
suppose plus 5 there was a constant, then it wouldn't have been 0, no, sir.
no, I'm talking about when both x and y equal to zero.
Yes, sir. Sir, here if the polynomial expression was ax square plus 2bxy plus cy square plus 5, then at
It
0
will
comma 0 it is not 0, it is 5.
okay, but do you think that you'll get that kind of equation?
In our matrix form we won't get, sir, but in general I'm asking the
General,
definition of positive definite function.
there is no such kind of thing, I guess, which is called as a positive definite function. It's like either it is a, if it is talking about matrix, I think it is positive definite matrix or not, right? I'm not sure
Okay,
whether it is there or not. Okay,
okay,
maybe
sir,
it's
no problem.
hmm,
I don't know, sir. The professor was explaining something I
okay,
didn't
okay.
understand. No
Don't worry
problem.
about, like, leave that part. Don't get confused yourself also, and like it is like going to haunt you for like some amount of
No,
time.
no problem, sir. Thank you, sir. Thank you, sir.
Okay, so I think we have talked about this right last time. Okay, this is okay. Maybe I'll skip this part. Anyway, I'll share this PDF with all of you. You can solve that. How to find out the okay. Okay, the maxima minima. I'll skip for now. We'll just talk about. I think you guys will be able to solve this, right? This kind of equations.
Yes, sir.
Find agent matrix all the time, so you don't have to do anything else. Right. Okay. Anyway, I'll share this with you. You can check your answers later on. Because I think some of you are having class at 8. Okay. Yeah, just try to solve this part. whether this matrix is positive definite or not, or whatever. You know the conditions, right?
Yes, it is positive definite.
So what is the
Sir, say
determinant?
the conditions, sir.
Okay, okay, I'll write down all four conditions once more. Mm, positive definite. Okay. So for that, the matrix has to be square and symmetric, right? There are four tests. First test is, let's say, determinant test. Okay. Let me talk about the 2 by 2 matrix, which is A, uh, B, B, and C. Fine. These are the elements of it. Then determinant of A will be, so this two determinant, right? This is first determinant, which is A is greater than 0, and the whole matrix is determinant, which is AC minus B square should be greater than 0. It is strictly greater than 0. Then there is eigenvalue test. Okay, eigenvalue test is, it will have two eigenvalues if it is a 2 by 2 matrix, and both the eigenvalues has to be strictly greater than 0. Third condition is the pivot test. In this case, the pivot test will say that the first pivot should be greater than 0. The second pivot, which is AC minus B square by A, should be greater than 0. And the fourth test, basically, it is a test, or you can say that it is a condition. So this polynomial has to be greater than 0. In that case, I should say that this matrix is a positive definite matrix. What about the positive semi-definite?
All greater than or equal to 0.
So this will going to be, what about this
That will
pivots?
be equal to 0.
Pivots, this has to be greater than equal to 0. Okay. You can check
One
for
of
the,
the
yeah, one of the pivots has to be greater than 0.
positive.
And one of the positive, and yeah. But yeah, let us talk about this. In this case, what is the determinant here? First determinant is 4,
4.
which is
4.
positive. The total determinant is 0, right? 8 minus, oh sorry, not 0, it
So
is
how it is
4,
also
4.
4.
Sorry, it is 4, sorry. So it is 4. So that also is positive. So both determinants are 0. That's going to be a
Positive
positive
definite.
definite. Okay. So this function, right, for any given x and y, it is greater than 0, and hence it is positive. The second thing is, a is greater than 0, AC minus B square is greater than 0. That is why a is positive. Fine, positive definite. Okay. What about this matrix?
Positive semi-definite.
Yes.
Positive semi-definite, right? Because the first determinant is greater than 0 and the entire determinant is equal to 0. You can check this way also. If you can find out its eigenvalues, then they should be greater than equal to 0. So you can see that one of the eigenvalues is going to be 0, right?
Yes, one is 4 and one is 0, I think.
Yeah,
Something like that.
correct, right? Yeah.
Not sure.
No, that is correct. So this is what it is, and see, you can see that a is greater than 0 and AC minus B square is equal to 0. So that's why it is called as a positive semi-definite matrix.
Sir, please share this deck, sir.
Yeah, it will be shared. So I think you can actually check with this, right? So it's going to be this
The
point.
tutorial video, sir,
Hmm.
in our the videos that are given, the last tutorial video, I think all of this is even
Yeah, it
Hessian
is
matrix,
mentioned, I guess. Yes, yes, it is mentioned.
Hessian matrix, everything is
Yeah,
explained.
yeah. You can check that also. I'll share this PDF as well so that you can practice it later on. Right? Okay. What about this? So A is greater than 0 or less than 0?
A is less than 0.
A is less than 0. What about its determinant?
It is greater
Greater
than
than
So what we call about it? So how to show it?
negative definite, I think.
negative definite, right? Yes, that's true. It is negative definite, right? Because determinant is greater than 0 and
A is
uh,
less than
a
0.
is less than 0. So it is negative definite. So a is less than 0 and ac minus b square is greater than 0. So is a negative definite. So what was the condition for negative definite? This determinant, right? Entire determinant should be,
Greater than 0.
yes,
Greater than 0.
and its first value has to be less than 0. So this will look like this. So it will have only one maxima. Right? Okay. What about this? Similar to that,
Negative semi-definite.
negative semi-definite, right? So when we have positive semi-definite, what was the condition there? AC
A
Determinant
should
minus
be positive.
negative.
and determinant, the entire determinant was equal to 0, right? So this is going to be a negative
Semi-definite.
semi-definite.
In
It be
negative,
indefinite.
Yeah, yeah. Tell me.
So shouldn't it be indefinite because determinant is coming out to be 0?
No, no. Indefinite will be when it is less than 0. The determinant is going to be less than 0. In this case, determinant is 0 and its first pivot, right? Or rather, I'll say that a is is less than 0. Hence, it is negative indefinite, negative semi-definite. I'll
sir,
show you.
in
Yeah, I'll show you that example also. Indefinite. Okay.
Yes, sir.
So this condition is there. A is less than 0 and AC minus b square is equal to 0, and hence it is negative
Semi-definite.
semi-definite.
Yes, sir.
so
What
what
about,
are the eigenvalues of that
you can,
negative semi-definite?
they should be what, like one of the eigenvalues is going to be 0 definitely, right?
Yes, sir.
Yes,
Another will be negative.
And other eigenvalues has to be
Negative.
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 Thank you.
Yeah. What about this matrix?
In
This is going to be indefinite because your determinant is going to be, you can see,
negative.
right? So minus 2
Less than
minus 4
0.
minus 4, it is minus 8, so it is less than 0, and hence it is a indefinite matrix, right?
Yes, sir.
So A is indefinite because AC minus B square is less than 0. So now it is clear, right? You do. I think you are getting the idea about like how to decide. So
Yes,
whenever
sir.
the entire determinant is less than 0, it is definitely indefinite. If it is equal to 0, then it can be either positive definite or negative definite, right? Then you'll have to
Yes.
see their
Sir, if it is
The
0,
sign
then
of
it
A.
should be.
uh, okay,
If
one second.
entire determinant is 0, then it should be the semi-definite. No?
Either it is
Yeah,
positive
that's all.
semi-definite or negative
Or negative
semi-definite.
semi-definite, right? Yeah. And if the determinant is greater than 0, like entire determinant is greater than 0, in that case you'll have to find out uh,
Let's say the positive definite
positive definite
or
or
negative
negative
definite.
definite, and it depends on that those values, right? The initial values. Okay, what about this?
Positive definite.
Positive definite.
Think about it properly.
Yes.
What is the determinant? Entire determinant. Okay, first determinant
6.
is okay.
6.
First is
One.
First,
A is greater than 0 and the determinant is
one is
6.
0.
Is
But what
also
about this determinant?
3.
2, right?
says 2,
2. Sorry.
2,
6,
and this is 6.
6.
So all are positives, right?
Yes, sir.
So then it is positive,
Definite.
Definite.
right? Correct. And you can actually check the eigenvalues also. So it's a diagonal matrix anyway. So what are the eigenvalues of it? Like 1, 2, and
1, 2, and 3.
okay, good. So let's
sir, in previous one, if anyone is negative, then it should be indefinite.
I think, see, if it's like one of the values here is negative, then definitely your determinant is going to be negative, right?
Yes, yes.
And if the determinant is going to be negative, so it's going to be, hey, any
Indefinite.
one value. If it is minus 1, then it is indefinite matrix. Okay. uh, okay, I think it is like solved using the determinant test, and you have seen, right? And this is eigenvalue test. So see, when you have 3 by 3 matrix, right, then it's better to do this two test: eigenvalue and determinant. Okay. What about this? Now this is tricky one. Think about it.
Positive semi-definite, right?
So here it is positive. What about this?
Semi-definite.
This 2 by 2 is
Determinant is 0.
0,
Second
and
one.
second and third is determinant 0, and the first is positive. It's going to be positive.
Semi-definite.
And what are the eigenvalues of it? From eigenvalues, can you conclude it?
1,
103. So eigenvalues are positive, right? And one of the eigenvalues is 0. So it is going to be semi-definite. So semi-definite, in case of semi-definite matrix, one of the eigenvalues will be 0, right? And other eigenvalues should be
Greater than
positive. Yes. I hope you are understanding now. And let's say if it was -1, -3 here, what was the case then?
negative.
Negative semi-definite.
Negative semi-definite or indefinite?
Uh, so negative semi-definite.
Yes, negative semi-definite.
Okay,
Negative semi-definite.
Because overall determinant is 0.
Overall determinant is 0. No?
Both determinant is 0 and A.
Yeah, right. So here the eigenvalues are 1, 0, and 3, and here it is positive semi-definite. If we found out the determinants is like a1 is greater than 0 and these are 0, so it is positive. Is that okay?
Sir,
Hmm.
sir, like if you can request one of the TAs, to just make bits and pieces of some, these kind of things, just before the exam, so it might help. So
Okay.
short notes kind of things.
Sure. Okay. I'll ask them to do that.
These kind
I
of
think
issues.
you can use this also. You can make your own notes, right?
Sure, no problem.
So
Just
that's fine. Yeah, I'll ask them also. Not an issue. Maybe about like at least the for each of the cases, right? You can write down all this. Uh, what do you say? Rules. What are the
So
rules?
negative definite.
Yeah. What about this?
So negative definite.
Definite.
Indefinite.
No, so negative definite.
Okay. Minus actually, right? So no. You see the determinant. What is the
indefinite.
determinant?
Indefinite. No?
It is indefinite because the determinant is negative.
It's a 0.
Indefinite.
So
Oh,
the negative definite.
why it is negative definite?
So because the eigenvalues are negative.
2 and -6. Okay. So fine. So it is like we'll have to check through eigenvalues here. So all our eigenvalues there, they are all negative, right?
So I
Fine.
think we'll have to check here for the
In this
data
case, yeah, no. In this case, when it will be indefinite is when all this determinant, right?
determinant, yes.
All determinants has to be negative, but we didn't check for this, right? The second one is positive. You got it. So we actually jumped to the conclusion by like looking at entire determinant, so which was like -6, right? Here it was -1, but you see for 2 by 2 it is positive. So it will be indefinite when all of this, right? Let's say this is a1, a2, and a3. That all has to be negative.
Negative.
Yeah,
Negative.
or you can
But
say
what about eigenvalues in case of indefinite?
eigenvalues. Okay. What it should be? Uh, if the all the all this will be negative, right? In that case, I think eigenvalues will be some of the eigenvalues will be positive and some will be negative, right? Is that fine? So let's say if it is 3 by 3 matrix, right? The eigenvalue should be like this. So one is, let's say, -1, this is positive, like 2, and this is going to be, so you can see that if it is a odd uh, odd order matrix, right? Let's say 3 by 3. In that case, what it should have, one
One
eigenvalue will
should
be positive and two should be negative. If it is
yes,
a even matrix, like 4 cross 4, in that case one should be positive and
one should be
negative.
negative.
Other three,
Oh yes,
it has
sir.
to be negative, right? Or vice versa. Like,
Sir,
yeah.
can you upload the link in the chat?
No, I ask them to upload it on the portal, or I can do one thing. I can attach it to the Gmeet only. Today's calendar, right? I'll attach it to the calendar.
Okay, sir.
Yeah. What about this? Okay, this is done, right? Okay, let's. Okay, this is the final one. Then you can stop. What about
Exam
this?
0.
So negative semi-definite.
This is
Negative
-1.
semi.
This is positive, and the entire one is 0.
0.
So
Negative semi-definite.
yeah,
Yes, negative semi.
right?
Yes, sir.
Okay. I hope it is clear now.
Yes,
Uh,
sir.
yeah.
Yes, sir.
So maybe after this session, I will attach this link here as well. You can actually get it from a portal as also, right? I'll make sure that it will get uploaded on the portal. Okay, that's it. If you
In the
have
portal,
doubt, yeah,
in the portal, like it will be uploaded in PDF format.
PDF format as well as that link
Okay,
also will be provided. Both.
Sir,
sure.
can you compare the matrix representation like 6.4 activity third question?
Can you tell me what is the question?
It was a metric representation. What will be the metric representation of the function?
Can you share your screen so that I can see
So
the question?
we can leave
Sir,
the session, right?
I am on mobile. That's why.
So
Eh,
can we leave the
I can
session
tell
now?
the question like.
you
So can
okay?
we leave the session now?
You can leave. You can leave.
Thank you, sir.
Yeah, that's fine. You can leave. So those
Six
who have
point
doubts,
four fifth question, sir.
6.4. Is it possible for you to read that out or no? No.
Sir, I will try to, sir.
Otherwise, I'll have to open it. It's okay. I can open.
There is the same question in graded also that in that
Yeah,
confusion.
that is 2 by 3, and this one is 2 by 2. I'm not able to get this xy because uh,
Yes, this
Okay.
is
standard form
because
is a square ax square plus
Let me see.
2xy.
What is the correct representation of this matrix form? Okay. Okay. I
also
understand.
in this matrix there is a problem because we have when we have xy then one more possibility is yx also.
Yx is
This is
what?
the uh, yx is one more the possibility is yx in this when we represent the matrix.
No, you generally you don't do like the opposite one. You just say that okay, there are two unknowns x and y, and that order is like this: x and y. The first component is x, and the second is y, and from there you will have to find it out. So you said it's not you're not able to. Okay, you can tell me that form. I'll try to get you the answer. Right? Just tell me that x square plus xy plus 2y square. Right? Okay.
Yes, sir.
You can stop sharing your screen. No issues.
Okay, sir.
Yes. Okay. So I'll tell you uh, how how this is going to be done, right? So you can easily find it out. That is, I think, x square plus what is it? Xy, right? Plus
xy, yes, sir. Xy plus 2y square.
okay. So any matrix, right? If you think about it, so it is A, B, B, and C, right?
Yes, sir.
Okay. And is it said something about positive? Is it whether it is positive definite or not?
No, sir. It's just matrix representation of in
Okay.
SVD.
Right. So, okay, no issues. So, let us consider this as ax square plus this is going to be 2bxy plus cy square. Okay. Try to do the analogy here. So,
Yeah, A will be 1, C will be 2, but what
a will be 1,
1?
hmm, c will be
Yes,
2, and 2b equals to 1, then b equals to half. Huh?
yes, sir. But there.
There is no option. This is the problem.
Yes, sir. That
No,
is not able to.
don't worry. No, that's not like that. You'll have to uh, make that into this format, right? So this 2b, you'll have to make that into this 2b, right? How you're going
Yes.
to do that? Uh, okay, maybe And what are the options? What is the correct option there?
xy in row, and then 1 minus 1 2 2, and xy in column.
These are the options. Correct option, huh?
Yes, this is the correct option. Like matrix is 1 minus 1 and 2 and 2.
No, no, I think that's wrong. Then
The same problem in graded also.
no, I think see there is a problem here. So I this see if you just try to solve this, this is not going to. I think there is some mistake there.
It is correct.
Huh? X
No, sir.
minus
In this 1 minus 1 in column.
1 minus 1. But
Yes.
still it doesn't matter because in that case also it's not going to. See, yeah, okay. Let us try to do this. So it will be
So
what?
the solution of this is not unique. So the diagonal entries are fixed, but
So
off
what are
diagonal
the
entries are can be varied.
x plus 2y and here minus x plus 2y, yeah?
Mm.
And that's going to be x square plus 2y square minus x square plus 2y square. And then how this is going to be the same matrix, right?
If minus y
So
in
it is
this
qx square, no?
equation, then it
X
is
square plus
possible.
qx square.
Okay. It's going to be x square plus 2xy minus 2xy plus 2y square, right? This is going to be x square plus y square. How that is going to be equal to this, right?
Yes, sir. And there is no option like
No,
b
no,
is
no.
equal to
Then
half.
no, no. The question is having some mistake there. That is
And
wrong
and
question.
the same problem in the sir graded assignment. There is 3 by 3 matrix, but same problem. There
Okay,
is
I'll,
no.
I'll look into that. I'll look into that. Okay, if it is wrong, then we'll give you the marks or we'll discard that question. Fine. So I think the deadline is there until today. We'll see from like tomorrow. We'll check. But this has not to be like this because this right this
So
coefficient they should be equal to this. Yeah.
so the matrix multiplication should be from the left to right, from the input to the output. You are, I think, doing in the wrong order.
What is it? No, that is okay. No, I think you can multiply
But
this with this and then
no, no, but the matrix multiplication is not commutative.
no, I am not doing anything right. I am just multiplying this matrix with this. How does it wrong? I'm not multiplying this matrix with this, right? Okay,
No,
let me
first, you
see.
have to do with xy
This one.
this middle matrix, and then with the third matrix.
And,
There is no problem in that.
there is yeah. So you try it out. It's not going to be like that. You are saying is correct. Like you are saying that I should multiply this with this, and then this with this, right? What I'm doing is I'm just multiplying this with this, and then multiplying this with this. That
The
is
number of column is equal to the number of rows. Only one thing is
yeah.
when you
That's
multiply.
that is not wrong. Okay, fine. Yeah. Okay then. I think we'll stop it here now.
Sir.
Yeah. Yes. Yeah. What is it?
Yeah, I have a question at the very, I mean, related to the very first question we solved. If we have time to
SVD.
discuss, yeah, yeah.
Okay.
If we have time, can we discuss
Yeah,
that?
yeah,
It's a
yeah.
bit
You
small.
can. Yeah, you can tell me. You
I
want me to
believe,
share my screen?
yeah, your notes will be
Okay.
good.
So for the same question, if you do the multiplication from the left side, I'm getting the answer. Can you show that again?
Arey, yeah, you'll get it. Just trust me, man.
I don't know.
How? What do you think? Like okay. You want me to do that? Huh? Let's see.
Yeah, but I'm getting the answer.
1 minus 1, 2, 2. Then you're saying that xy. Yeah.
What was the equation?
This was it, right? Okay. Let me do it.
X
This is
square.
okay. This is 1 cross 2, and that is 2 cross 2. So I should get 1 cross 2, right? Then I'll get like this. What should I get here?
X minus y.
Minus y here. 2x
3x
plus
plus 2y.
here it is xy, right? And that will be
X square minus y.
X square minus xy plus 2xy
X square minus xy.
square minus xy plus 2xy
Y.
plus 2y square
Okay.
x square
X
plus
square plus
xy
2y square.
plus 2y square. What's the equation? Is
This was, yeah,
this
this was,
one, right?
yeah.
This was the equation we got now.
Okay.
And so even if you exchange this off diagonal interest, we'll get the same answer. It doesn't matter.
Hmm.
So the
Okay, let me
solution
think
is
about
not
this.
equal to this
See,
one.
but the thing is, if I
Hmm.
understand it correctly, right? This thing x square plus xy plus 2y square, right?
Hmm.
This coefficient has to be the coefficients of this. But okay, let me see that. But
Yeah, that is for this x square and y square only. But for this xy, it should be sum of these off diagonal entries. Coefficient of xy should be the sum of off diagonal entries.
okay,
A bit easy.
okay, let me go through it. Maybe I'll clarify on this whenever we'll meet in the next session. Okay. Yeah. Okay, I understand. Okay, let me see that. Okay. What was the question? Again, like, can you just tell me? Okay, this first question we were talking about, right?
Yeah.
What is the problem here?
Yeah. So in that, did we assume that you and we are the same?
Same in the sense?
I mean, the equation is A equal to U
Huh?
sigma and V transpose, right?
Okay. A equal to U sigma and V trans. Yes.
Yeah. And U is the eigenvectors of um,
A
what's
transpose.
yeah, A transpose, and for this it was A
A trans.
transpose A. So was this a special case where we have A transpose equal to A transpose A? I did not actually understand. I mean, we didn't find when we solved this, right? You wrote B. Where did we find U? I didn't see that. Yeah, that was
Okay.
my
Okay.
question.
I'll tell you the eigenvectors of A and A transpose and A transpose they are not same. The eigenvalues of them are same, right? I'll just write it
Okay.
down. So the eigenvalues of A transpose A and A transpose are same, right? Okay.
Okay. Why
So
is that? Maybe that is one part which I missed.
yeah, so A transpose A, if I find out the eigenvalues of it, right? I don't need to find out the eigenvalues of A transpose. Okay.
Is it always like that, or is this
Yes,
this is
always, always, always. That is not a special case. It is like always for all
okay?
any kind of matrix you take, you just do A transpose A and A transpose. The eigenvalues are going to be the same. Okay,
Okay.
but the eigenvectors of A transpose A and A transpose are not same, right?
Okay. Okay.
Okay, so once you find out the eigenvalues, you can use those eigenvalues to get the eigenvectors of A transpose, right? Because
Got
anyway
it.
they are same. So I don't need to find out the eigenvalues separately.
Okay. Okay.
One more thing is, let's say x1 and x2. Let's say these are the eigenvectors of A transpose. A transpose A. Fine.
Mm.
Lambda 1 and lambda 2 are the eigenvalues of A transpose A. Suppose in
Yeah.
that case, what will be sigma 1 and sigma 2?
Square root of
Zero.
lambda one.
So these sigma 1 and sigma 2 are also the singular values for A transpose, right?
Correct.
So if I have the eigenvectors for A transpose A and if I have these singular values, there is another method to do that is what? Like I will find out, let's say y1 and y2 are the eigenvectors for A transpose. Okay? Then
Mhm.
y1 will be, I can find it out by using this 1 upon sigma 1 A x1, y2 is equal to 1 upon sigma 2 ax2. This is also a way. This
I think I lost. Okay.
this is the
Uh,
Grant Smith way.
okay.
Or you can do what? I know the eigenvalues for A transpose A. What I'll do is I'll find out
Can
the
I stop you there, sir? Can I
yeah,
stop you? What was y1 and y2?
they are the eigenvectors of A
Ah,
transpose.
okay.
So like x1 and x2 are the eigenvectors for A transpose A, right?
Okay.
I can directly find y1 and y2 if I know this sigma 1 sigma 2 x1 x2.
Okay. Okay. Got it. Yeah.
Or if you don't understand this part, you what you can do is you just find out the eigenvectors for A transpose.
Transpose. Okay. Okay, in this problem, did you really solve for you? I didn't see that
No,
you
no,
make
I
it.
didn't solve it.
Yeah.
I think I just I just solved it till V transpose, right?
Oh,
And after that I didn't solve it. I
okay.
think, or okay, I have solved it. Okay, anyway, I solved this for like this way. I solved it
Ah,
this way. One
okay.
upon sigma one ax1. I found out this was y1. Okay,
Okay.
1 upon sigma 2 ax2. I said this is going to be zero, right? Sigma 2
That
is
I
going to be
remember.
zero,
Yes. Okay.
and then hence, but they anyway they are the orthogonal vectors. So
Mhm.
if I know this is 1 by root 10 and 3 by root 10, what will be the orthogonal vector to this? Minus 3 by root 10 and 1 by root 10. And now what is u? Your u is 1 by root 10,
By root in, 3 by root in,
3 by root 10 minus 3 by root 10 and
1 by
3 by root 10. And what was your v? V
the
was
earlier. Yes.
this was right 1 by root 5, 2 by root 5 minus 2 by root 5, 1 by root 5, and the v transpose will be this,
Got
right?
it.
And now
Yeah.
the SVD form of it is what?
Now we can multiply.
Yeah,
Yeah.
SVD of A is 1 by root 10, 3 by root 10, minus 3 by root 10, 1 by root 10. This sigma matrix will be root of
Plus
50,
50,
0,
0.
0. And then this was, I think, B transpose was, what was that? Yeah, 1 by root 5 and minus 2 by root 5.
Yeah.
1 by root 5 minus 2 by root 5. Here it is 2 by root 5 because this is like orthogonal, right?
That was clear. Yeah.
And then if I just multiply everything here, then I should get the original matrix A.
Yeah. Yeah.
Okay?
Yeah. Thank you so much, sir. Yeah.
Okay. Bye bye.